Well, my name is Joseph Wunderlich. I'm a professor of engineering, architecture, and computer science. This is a lecture on cache design, including three different source textbooks, some written problems, reference to work that I did at IBM, research on large-scale System 390s, as well as a reference to a paper I wrote when I was at Purdue University. I've been a full-time professor now for almost 3 decades. And at the end here, we're going to have some updates in 2025 of the H100, which at present time is the highest performing Nvidia chip, and look at some of the cache optimization techniques that they do. This is an overview that the students will look at the end, and I'd like to just talk about a little bit in the beginning. We're going to optimize cache design with different mapping techniques, as well as cache block size, and then look at some of the latest 2025 H100 Nvidia chips and their optimization methods. This is something that I published in the late 1990s. Looking at microcontrollers. I was a professor at Purdue University right after leaving IBM research, and I wanted to give something to the students for educational purposes, showing them a basic minimal computer architecture for all computers, from the smallest little microcontrollers to the large scale systems. So this abstraction applies to all cases. That's the intent. And most of my students, by the time they get to cache design, have seen this in some way. So here's an example of that microprocessor versus microcontroller in the boundary. Microprocessors will, in PCs, for example, be on a motherboard with main memory in RAM, random access memory, and then static RAM inside the processor, and then different speeds that the processor runs at versus memory versus the board. The board's going to be the slowest. And then caches are in between. In a microcontroller, it's all a single chip. Everything's in there. There's really not a lot of difference, or really not at all, between memory access and register access, because it's all a monolith of static RAM inside. Now, you can do external memory with microcontrollers, but typically the idea is to do everything in one chip.
Another important review topic is the whole rationale behind caching, and it's based on probability and more specifically temporal and spatial locality of reference. So temporal means you just did something recently and you want to do it again. Most likely you are going to want to do it again, so you put it in a cache close to the CPU. Spatial has to do with how much you grab when you don't find what you want. When you don't find what you want in the cache, how much do you grab from main memory and then put into the cache? So in all probability, you're going to want something, if you're not using exactly what you just missed getting recently, you want something close by to that. So what that means is, if I just was in an instruction, I just used an instruction, and I think I'm going to use it again, and it's not in the cache, I go and I get a whole giant chunk of code out of the main memory as a cache block, and I drag that in, because in all probability I'm sequencing through a code segment, and I'm going to use things that are sequentially located right next to each other. Also in data, if I was looking for a piece of data, say in an array, and I looked in the cache and it wasn't there, I don't just go and find what I want out of memory and put that into the cache and bring it in the CPU. Also, I get what I need from the CPU, bring it into the CPU, from the main memory, what I need for the CPU, I bring that into the CPU, but simultaneously I replace the cache block with a chunk of data, like an array, not specific boundaries for the array, but in all probability a block size that will cover a typical array, and then put that into the cache. So that's the two main topics there. And then below here are just basic architectures, which I hope you know from a number of places already, is how our SMP lays out, symmetric multiprocessing. Think of it just like shared memory processing. So your processors are all talking to main memory via caches. And just show one cache here in each of these, but there's layers of caches, levels of caches. And then MPP is just kind of like a big computer network, but it's inside one box, inside one case. And a lot of the new supercomputers, the PCs not quite yet, but PCs are all SMP kind of architectures. And a lot of the supercomputers still, the enterprise servers certainly. But we're going MPP with all the giant number crunching top 10 supercomputers now. And so I'll have to check on that. That changes all the time, but I'm assuming there's still MPP, which is where the processors are all talking to each other, and then each processor has its own cache or levels of cache and memory, essentially like a bunch of PCs connected on a network. Now there are exceptions to this where the memory, you can actually communicate between memories with direct memory access between the processors, between the nodes in the MPP machine. But this is the basic architectural difference. Firstly, we are picking CPU. Next, we want to talk about RAM. Selecting. Now, here's a diagram which is a common way to show the levels of hierarchy of memory. Now, remember, memory, quote unquote, memory means your RAM main memory, and that is an industry standard reference. However, when you drill down into the details, all these things are types of memory, so that can be a little bit confusing sometimes. Now, there's levels here, and the levels at the top, the registers, that's static RAM, and that's inside on the chip piece of silicon. It's very fast, and you know how those work from the review materials. Then the next level is going to be faster with this is cache, and this the level, there's actually 3 levels of cache, but just grouped together here as cache, and that's also static RAM. Then main memory, and those are DRAMs, you know what that is. And then storage, right? That's not, that's a separate thing. It's a type of memory, but it's that's your hard drives, your optical drives, your flash drives, solid state flash drives. Solid state means no moving parts, so so we learned about that in other places. The magnetic drives are mechanical drives with moving parts, and so that is going to break over time. But sadly, the solid state will actually break down over time also, but much less frequently than things with moving parts. Mechanical things break much faster, typically. And then tape units. So tape units, you don't see that a whole lot, but be aware that the college backs up everything on all the servers and all your information and everybody else's, and puts it into Iron Mountain, I believe is the name of it. It's a secure place close by, and all secure things in the country are backed up in vaults underground, and tapes. Huge terabytes and terabytes of information. At IBM, we had something the size of 3 basketball courts for backing up all of our design and test information that we do for the supercomputers, and it went back. See, I was there in the 90s, so that was from the 50s. So I had 40 years of stuff in there. I had there's something the footprint of 4 basketball courts, 2 stories tall, library like Carol's, full of tapes, with a robot on a railroad track that would run and reach up and put it in. You'd get out of its way. You wouldn't go into the facility. You just put your thing through the slot, and you'd see the robot grab it, run down its railroad track, run between the aisles, and reach up and put it in. Pretty cool to see in the secure area. I mean, you can't get a field trip there or anything like that. It's very high security. You have to badge into the site, badge into the building, special access to get to the test facilities and research facilities. Armed guards and a helicopter flying around in a circle all the time. But it's pretty cool to see. So anyway, this is, you can see now on this thing, it's drawn, it's shaped like a pyramid. Actually, if you're going to do it to scale, it'd be much wider on the bottom here, but that's capacity on the bottom. And then as you go from top to bottom, you have increasing capacity and access time, so slower. If you have more time to access, it's slower. So you get slow down the bottom, but you can pack a lot more stuff in. And also, you see on the other side of the diagram an arrow going up that it's costly, more cost per bit. Static RAM is more expensive, and that's why you don't make everything out of static RAM. And a tape is relatively, per unit of storage, much cheaper. Much cheaper. Okay, now we want to begin understanding this at a little deeper level. So, dissecting that last diagram, or perhaps expanding it, you can see now the registers and how things lay out. So we're going to look now inside the cache in this lecture quite a bit, and we're going to understand how things lay out in the cache, different mapping techniques and mapping between main memory and the cache. And it's not a trivial thing. We'll take some time and really look at those and design different things. A couple of things you want to note here is to start talking about cache blocks here up in the beginning, and there's an optimal size of that. How much do you really grab when you have a cache miss? How much do you go and put in that cache based on spatial locality of reference? And there's an optimal size. You don't grab a giant, super big thing more than you need, because then you're going to fill your cache up, have less cache blocks, and increase the miss rate when you're looking in caches, right? Because you only have so much size. It's expensive little memory. And they also speak of words here, and they say 4 bytes. That varies on machines. You got 2 bytes. You got byte addressing. That varies. In IBM, we had one thing. The PCs are another thing. Microcontrollers are another thing. Everybody has something different. Well, not everybody, but all the machines could vary what a word means, and it actually varies between processor families too. Motorola and Intel the past 30 years. So just be careful when you ever see word addressing, what's meant there. You'd think there'd be an industry standard. My experience didn't settle down to one at any time in the past 30-something years I've been in computing. Actually longer, because even the building industry and built high-tech companies, built high-tech buildings for companies, built buildings for high-tech companies, computer room floors and such, starting early 80s. Story for another time. So now page size varies. Now you may say, what page? Remind me of what a page is. So remember, you only fit so much into your real memory. So you remember your virtual memory. If you don't, maybe need to go back and review something somewhere else, another course. But virtual addressing, virtual memory is a very important concept. I'll briefly just state it here. You have a 2 to the 64-bit machines, where we're at now. You have 2 to the 64, which is a huge amount of address space that the programmers and the operating system thinks it has. The CPU thinks it has. And nobody wants to burst the bubble and say you don't, plus you make good use of it. However, you only have, in reality, much less of real memory that can fit, for example, on a PC. 2 to the 40 is 2 to the 10 times 2 to the 30, which 2 to the 30 is a gigabyte, billion bytes. And 2 to the 10 is about 1,000. So 1,000 gigabytes is about the most real memory you're going to fit on a PC motherboard. And so you've got this monster 2 to the 64 thing, space. And so you have to translate. So there's virtual address translations, and that's something in this course we're going to touch on, is actually caching those translations every time you look for something in real memory. So you say, where are you going with this? Well, this is the idea of paging. Paging means you may not have what you want in the real memory, right? You have this huge monster address space that the programs and the CPU is playing with, but you don't actually really have it there. And so you may not have what you think in memory at a given time, the CPU thinks. And so you get a page fault, which means you got to go get another chunk. This is not a cache block chunk, but a giant page chunk out of storage, some kind of storage. And you got magnetic or optical or whatever, even in disk storage. You got to go get it someplace. Even tape storage. You got to go get it from someplace, or solid state storage. You got to get it and put it into RAM. And so, paging. So you should understand now from this slide and from things in the past, a little bit about words and what that means. Beginning concepts of cache block, and now pages. Now, perhaps I'll show you something I did as testing this and other parts of cache design in IBM. I wrote an internal report. It was IBM classified for many years, but this is a long, long time ago, decades ago now. So perhaps I'll show you. I won't print it, but you could see how testing this, and it's not just single caches. Remember that there's virtual addressing involved, of course, but now I'm talking about it even back then, many decades ago, before you were born, when, oh, I don't know, some of you were born, but in the early 90s, there were 20 processors on a given board, up to 512, so I'm testing 20 processors at a time, each with multiple levels of cache, in addition to virtual address going on, and I'll maybe show you that. But this is, so now looking a little more detailed, and also segments. So yeah, we had tables inside IBM. I mean, it gets complicated. I don't want you to know every single possible detail of what's going on, but it wouldn't hurt to know a little more, which we will be doing, of course. So now, quickly reiterating some of what we just talked about, you have a relatively large and slow main memory, and then you have these faster cache, and then the cache contains a copy of, not chopping a piece out of main memory, and then when the processor wants to read something, a word, for example, of main memory, a check is made to determine if the word is in the cache. If it's not, then a block of main memory consisting of fixed number of words, and how big that is we want to optimize that, is read into the cache, and the word is also delivered to the processor. Two simultaneous processes, not sequential. I mean, they're same time you have both of them delivered to the CPU and replace the cache block. If you're going out to the main memory to get it the first time you're getting it. And because of locality of reference, both spatial and temporal locality of reference, the spatial is the size of the block and the chunk you get, and the temporal is the whole rationale behind doing all this for future references. Then down below here, each line includes a tag that identifies which particular thing. So, the size of the tag is something you're going to spend some time on because it varies by the mapping technique, which you're going to learn in a second. And so there's a tag. So each line includes a tag that identifies which particular block is currently being stored. The tag is usually a portion of the main memory address. So that you're going to drill down now. We're going to understand how to address main memory, and also how these tags represent a portion. You say, why a portion? Well, you'll see. It varies by the mapping technique. So now we want to look at the details before we go into mapping techniques of how the cache relates to memory. So you see cache on the left, memory on the right. Memory has a number of address lines, 2 to the n address lines, right? Like 2 to the 40, for example, in real memory in a PC. But it says, up from 0 to 2 to the n minus 1 because the very last one is all ones, 40 bits of ones, which is 1 less than 2 to the 40, and then you still have 2 to the 40 bits. I mean 2 to the 40 of address space because you count 0. 0 is actually a location. So when you do counting outside the computer, you normally don't count 0 as a thing, but it is a real address inside the computer. The same on the left here, where you see the number of lines, spaces in the cache. It goes from 0 to C minus 1. So C is the number of lines, and that's where you're going to put your cache blocks. So your cache blocks go into the cache lines. Sometimes the block and line is used synonymous, but know that the lines are the locations where you put the blocks. And the blocks are chunks of main memory that you're putting a copy of into the cache. So, how many lines can you fit in there? Well, that's C number of lines, and then you see this C is less than thing. That means much less than the number of blocks in main memory, which makes sense because it's a smaller, faster memory. You're not going to fit everything in there. And then, therefore, you need to keep track of what is actually in there, and how you do that is with a tag. So you're going to have to define, design these caches and decide on the size of the tag. Well, it'll be decided by how you parse everything up and what mapping technique you use. But you're going to have a tag, and it varies by mapping technique, the size of it and how it works. So we'll see that coming up. But regardless, there's a tag of some sort identifying what block you're referencing, from main memory. And what block you're not only referencing, but you've taken a copy of it and stuck it in the cache. You don't cut it away; it's still in the memory, but you have a copy of that piece of main memory block in a slot in the cache. And now we want to keep track here, and this give an example. One word equals 2 bytes, and we'll use that as a default convention. But we'll talk about also byte addressing. But we'll just stick to the convention that a word is 2 bytes, even though that can vary by example. And I might show you some examples where that does vary. And you, outside of this lecture, will certainly see people use what a word is loosely. Certainly in the literature over the history of computing, in my experience, and computing for a million years, seems like now. So yes. Now we see a flowchart describing the behavior of the cache controllers. So the first thing that happens is you receive an address from the CPU. The cache controller does. And then you ask yourself, is the block contained in the cache or not? Well, no. That's a miss. If it is, it's a hit. Hit-miss ratio, right? If it's a hit, you just feed it over to the CPU. You got what you want. Now, if there's a miss, it's a little more complicated. So you got to go now to main memory. You've got to have already decided what size block you want. That's part of the way you've set up your cache controller and your mapping technique. And so you get a block. You go to main memory and you get a block, and then you decide which slot to put it in. That's part of the replacement algorithm. There's different replacement methods. It's not trivial. There's actually a number of different replacements algorithms that we'll talk about. And so you put it in the cache line. You put the block in the cache slot, the line, and then you simultaneously deliver to the CPU what it wants and put that block in. That block that's been allocated, you put it in the main memory. So again, if there's a miss, you access main memory for the block. You look there. You allocate a slot. You figure out where you want to put it, what cache line you want to put it. That's your replacement algorithm. What do you want to throw out, right, of the cache, and and right, that's just as important as where it physically goes. More important, actually. And then next you branch to do two things simultaneously. You give the CPU what it wants, and then you load that block from main memory into the cache line slot. Then down below here, we're talking about cache size. So you'll see this very important table down here that of all the things we're going to learn about coming up. And so before we drill down into all of that, I want you to just get the basic idea here. We'll start out with cache size, and then it's best to take a break here and digest some of this. Perhaps have a Zoom meeting and just discuss it in addition to working on your projects. Give you time for that. But anyway, let's just look at, let me look at the table first, and I'll come up here and talk about cache size. So the table, these are the 6 main things that you want to consider for designing your cache. So how big it is, certainly. Then we'll talk about that. And then the mapping function. So there's a good deal of detail you'll see coming up and several examples of each for you to look at. Different textbooks, and then one student wrote up a little thing for me. One of my teaching assistants just kind of taking notes from what I said. And before we had narrative, I found that helpful. Even when we have narrative, this audio, I think you'll find it helpful to look at a student's notes. And so we have different mapping techniques: direct, associative, and a set associative, which is sort of a compromise between the two because there's plus and minuses to direct versus associative. Set associative is somewhat of a compromise of the two. Then replacement algorithms, as we mentioned above here. What do you bump out when there's a miss? You got to get a new block. You want to get that block from main memory, put it in a cache line slot. You got to bump something out. So how do you do that? Least recently used, first in, first out. You remember this maybe from data structures kind of courses. If you took system program, if you're computer science, you have data structures course in our curriculum at eTown. You should probably learn this also in other programming classes or systems programming, which when we developed that, merged part of data structures course into it. Least frequently used, another data structure thing, and then random, right? So then you're dealing with probability there. If you're going to do something random, you should assess how that affects the probability of success, right? It's not just saying we don't care when you do things random. You're actually doing it in a deterministic way. That seems like an oxymoron there, deterministic randomness, but it's not, I can guarantee you. We're going to have a whole lecture and publication and things that got patented that I created inside IBM just for that controlled randomness. I don't want to go off on a giant tangent here because it's a whole couple lectures, but to do things inside the computer, and so you'll see I've got 6 correlated random number generators in there. They're complex things. Some of them are combining generators, some of 2 other ones. There's one you have a giant seed array that you randomize in itself and then pick out of that to seed the generator. So anyway, random is not arbitrary. And then number 4, write policy. So, when you have a miss, what do you, or when you're when you're writing, to memory, how does that work? Do you replace things in your cache when you're writing to memory? Well, you need to keep some consistency, cache coherence, cache coherency policy. Some of you, I've showed this expensive book I bought when I was working at IBM just because I had to write a program on cache coherency. You say, well, why is that complicated? Well, if you have an SMP machine, symmetric multiprocessing, shared memory, the caches and all the processors are potentially working on the same piece of data, and then you have 3 levels of cache on each processor. you can have some conflicts there. And so if a given processor grabs a piece of data out of main memory and puts it in its cache, and then is writing back to it and changing it in its own cache, and then plans on changing it in memory. Well, you better invalidate all the other processors' caches if they're thinking of doing the same thing, or block them out to begin with. That's not a trivial thing to make work. You could imagine trying to do this at lightning speed inside the computer. And the whole idea is to speed everything up. These are all speed up measures. So perhaps we will be drilling down into that. The line size, right? Essentially your block size, right? How much you can fit in. And then the number of caches. So there's different architectures here. You can have several levels also. You also can have shared. So some of the levels sometimes are interleaved, so you're sharing between processors. You also can have separate instruction cache from a data cache. Believe me, it gets extremely complicated, and I spent much of a month or more just on cache coherency inside IBM. So we're not going to spend a month just on that one thing here, but you're going to get an introduction to it. All right, so this first time I'm making this audio lecture, I'm going to intentionally not put audio on the remaining slides because I want you to just get a primer here and this is plenty for a day. And then what we'll do is after this, this first part of this lecture, I'd like you to get with your groups as we typically do. Now, I might modify this in future years, so let that modification override it if you see that in future years. But for this first offering of this audio, we're going to leave the audio off for the remaining slides. And of course, later on, they'll all be in there 2 years from now. I'll teach the course again. But for now, we're going to leave the audio off. You can plan on getting together with your groups online, right? So this first offering is happening during the whole coronavirus crisis, where just days ago we were notified to put everything online. So this is the first offering of this first lecture in this course. Just a week ago, it was announced we were going online and canceled all classes for a couple days to give everybody a chance just to do this. So anyway, after this, in this first offering of this course, go and Zoom with your teammates and do the online, finish the last online, last lab project, which we went to all simulation and tabled all of your circuits that you were building and your PLC or your hardware descriptive language FPGA stuff and your breadboard with all your wires and chips we just left sitting in the lab in 2020 on March, whatever day that was, when suddenly declared everybody in the country's going online to stop the spread of this virus. Hopefully 2 years from now this will just be kind of a annoying history note, but anyway, so we'll do that, and then just watch for my email and reply all to the email main thread. Remember, use the main thread. If you want to ask a question while you're listening to this lecture, you should be starting. Well, I'll put this on the email. So, I think you know what to do. And that's good for this slide. We have a diagram here at the top of this slide, which just gives you the organization again. You can see the cache and the processor, and main memory is located somewhere off on the bus, the system bus. And then there's control lines. So you understand address and data lines, and there's control lines, and there's a cache controller someplace overseeing all of this. You see buffers there in Engineering Computer Science 333, Digital Design Assembly Language Interfacing. We talk about those, and we use those on breadboards. They're tri-state buffers. You can't just connect everything to a common bus without having some kind of isolation. So you turn them on and off when you want to communicate. So we learned about tri-state buffers in there. It's not for this course. Now we want to look down into the details now, and first cache size. There is, a bigger is better. These some educational examples here, which are smaller, of just for education, and then we want to optimize that. Now, a bigger one will be have a larger number of gates, which we're going to see why in a minute, and then also can be a little bit slower too. So there's an optimal size. And it does, the caches get bigger and bigger over time, of course, but so does main memory. No matter how big our main memory gets, we tend to use it up. So we always need smaller, faster cache. I had a professor 30 years ago tell me that wasn't going to be the case because he predicted that memory would get so fast and so cheap you wouldn't need these intermittent or intermediate speed up memories closer to the processors or cores. Processors and cores are the same thing, remember. Um, and so, but that didn't happen. So just expect in your lifetime you'll still probably need caches. Um, so first, that's the mapping technique, or that's the cache size. Now let's look at mapping technique. We're going to look at the three different kinds. Direct associative and set associative, with set associative being somewhat of a compromise between the pluses and minuses of direct and associative. We're going to have this common example here, and we're just going to, for educational purposes, just say a small little cache of 64 kilobytes. And then the data is then transferred between main memory and the cache in blocks of 4 bytes each. And that's just another arbitrary setting. That's a rather small little block. This means that the cache is organized into 16K equals 2 to the 14 lines of 4 bytes each. You can do the math there to convince yourself that is right. You can take log base 2 of both if you like. Both sides of that to prove that 2 to the 14 is 16K. Otherwise, the rest of that should be obvious. The main memory consists of 16 megabytes, right? That's the declaration for this example, which correlates to 24-bit address. You remember from maybe other classes, engineering CS 230, that 16 meg. You know that a meg is 2 to the 20, and kilo is 2 to the 10, tera is 2 to the 30. You just memorize that. And then you can just look at this and know that, oh, well, 2 to the 4 equals 16, and then 2 to the 20 is a meg. And you know from your math, hopefully, that 2 to the 24 equals 2 to the 4 times 2 to the 20, right? You add the exponents. Thus, for mapping purposes, we're going to consider main memory to consist of 4 meg blocks of 4 bytes each. Okay, now we're going to go on to the direct mapping cache first. So here's our first example of mapping. This is a direct mapped cache. And byte addressing, you could have word addressing here, but this one's byte addressing. That makes a difference on how all the bits will lay out. We're given that this will be a 16 megabytes of main memory, and therefore that breaks that into an address space of 24 bits, as we discussed in the last slide. And then how that looks in hexadecimal. So there is 0 to 24 bits, right? Each hexadecimal character digit is not character, but digit is 4 bits. So that. Also, we're given that this is a 64 kilobyte cache with 4 bytes in each line. So the block size is 4 bytes. And in memory that we're putting in the cache lines, the slots. And so, therefore, 64K divided by 4 equals 16K of lines requiring 14 bits of address. This is in your cache. So your cache, this number of lines that are in your cache is going to be that many. And we'll need that correlates or corresponds to an address range of 0000 to 3FFFF. And so now you lay that all out. So you should draw that in your examples. Convince yourself that that makes sense. And you see an address space here of main memory and of your cache in these drawings. And then and with some examples in there of you don't have to do all these examples. You just see how things are laying out and what's in there, and the addresses are outside the box, and the data can be instructions too, but data instructions in the cache and in the main memory. First thing we want to figure out is the size of the tag. The tag designates, remember, designates where this block came from in memory, where this copy you've taken from main memory, a block, and put it into your cache. And so we want to figure out the size of that tag. Now to do that, you have to consider everything that's in there and what it represents. So you're going to have a line, you're picking which line and then picking which byte. And so since we have, going up here on the left here in the text, since we have byte addressing and each line of the cache has 4 bytes, we need 2 bits to pick which byte we want. Once you've started looking at once you've grabbed what you got and the CPU's got to figure out what to do with it, it looks in there and says, okay, here's the the byte addressing. So we want, read this again, we need 2 bits to pick which byte we want if we have a cache hit. And since we need 14 bits to pick a cache line to examine, right, that leaves us with, leaves us with 24, which is our original number of bits that the CPU is addressing main memory with. So 24 minus 14 minus 2 is 8 bits for the tag. So then we know the size of the tag, and therefore we know how to split up memory into groups of blocks. See, that's a trick here. Groups of blocks, and then there's going to be, in each block, there's a corresponding same block. In each block, there's the same spot in each of the blocks that corresponds to 1 slot in the cache for the direct map. This is how this works for direct map. So you might look at that again. Then there's another lecture, handwritten, coming after this. You can look at that again. But this, that's the gist of the difference here. Is this part. Therefore, we will split up memory into 2 to the 8 equals 256 groups of blocks, with each having a size of 2 to the 24 minus 8 equals 2 to the 16 equals 64K bytes. So you might want to look at that over and over again to make sense of that. Then, okay, so assuming that all makes sense, this is how it works. Down below here, it says when the CPU attempts to access memory, the 14-bit line part of the address is used to select a cache line to examine. Then the tag of that line is compared to the tag and the address from the CPU. Okay. If they match, it's called a hit. Okay, good. It's in. So you look in the memory. Our CPU is looking for it. It's in the cache. It's a hit, and we use the 2 bits at the end of the memory address to pick a byte from the cache line to send to the CPU. All right, that's good. Now, what if it's not in the cache when your CPU is looking for it? If it doesn't, if they don't match, it's called a miss. And we use the 22 tag and line bits of the address from the CPU to get the 4-byte block from memory to put in the cache line. We also simultaneously get that byte from memory pointed to by the 24 bits from the CPU and deliver it to the CPU. So you go back and look at your flowchart of the operation, make sure you understand that fully, then think about this and think about how this is parsing the memory into different these different parts here, these groups, and then how the direct map is working. And then look at those. Look at all the numbers here and addresses, and make sure that makes sense to you. Now, before we move on to the next type of mapping, associative mapping, let's look at a very important negative about direct mapping. In direct mapping, there is a thrashing problem. Thrashing is, for example, if we're saying A equals B plus C, and if B and C are located in memory locations that both map to the same cache line, so like there's different groups, right? And each one of those groups has a spot in there that maps to a certain line slot of the cache, then B and C will be repeatedly replaced by each other in one cache line each time A is calculated. So you might be repeating A equals B plus C in a loop. This is thrashing. Now, I wrote a program inside of IBM for our large-scale multiprocessor supercomputers doing this, and intentionally trying to thrash the heck out of all the caches and just to try to break the machine or slow it down so as to find a way to to find problems. We actually have this happen at the same time as page faults and other things. These unlikely scenarios, so we could maybe break the machine so it doesn't break for the customer, and then find ways to fix the break. So that's the idea of what our custom kernel and the APIs and everything that that developed, patented inside of IBM several decades ago. So anyway, this is a problem. This is that's a negative of direct mapping. I'm asking, if you do an essay question of pluses and minuses, or just at the end of a design problem, what's the minus of direct mapping? If I ask you to compare associative and direct in a little essay, and then other than the full design, which you need to do too, then that's a negative. Now, the associative mapping overcomes this disadvantage, but at a cost, of course. There's always a cost, and you have to weigh the cost versus benefits. Associative mapping overcomes the disadvantage of direct mapping because each main memory block is loaded into any line of the cache. So there's not like groups that have the same spot in there, each respective group pointing to the same slot, line in the cache. So you got everything in memory pointing, having a separate line that can be it could be in anywhere. And so now the tag uniquely identifies a block of main memory, and then the cache control logic, what it does is simultaneously examines all the cache line tags for a match. Now that can get very large of a comparison. You've probably designed comparators in courses for me, or maybe somewhere else, I don't know. But certainly for me and other courses, the prerequisite course of this, so you have a huge comparator there that takes up real estate, of course, in the chip and the silicon. It's also slower to do that, so you get both space and time cost for the benefit of not having thrashing. Okay. Now that we have looked at direct mapping for cache, we look at a fully associative cache, and with byte addressing, and everything else is the same as the last example, direct mapping. With 60 megabytes main memory, 64K bit cache, and then how many lines required in the cache, and the way the address space lays out. And look at that again and convince yourself those addresses make sense. Look on the diagram too, make sure that makes sense to you, because you will have to draw this test. And now, just like with the last example, we need to figure out the size of the tag, and then that tells us how many bits are laying out where. Now, this is different than direct mapping, since all the tags in the cache are compared to the tag in the memory address from the CPU. There are no bits in the main memory address used for selecting a cache line to analyze, right? So that's different. And we'll go back and compare the difference between the two, maybe right here, make sure that makes sense to you. Pause this and go back, make sure that makes sense to you. Therefore, we only need 2 bits of the main or of the memory address to be reserved for picking the byte from the 4 bytes in the cache line. And therefore, the size of the tag is 24 minus 2. It's 22 bits long. This makes sense since there are 2 to the 22 different 4-byte blocks in memory. Think about that. Make sure that makes sense to you. When the CPU, and then down below here, okay, so you lay this all out, look at the different numbers, the data examples that are in there, make sure that diagram makes sense to you, what this figure is showing. And then, so how this all works down below, when the CPU attempts to access main memory, the 22-bit part of the memory address from the CPU is compared to all cache line tags for the associative mapping cache. If they match, does it hit? Yay! And the cache is working, so it did its job here. And we use the 2 bits at the end of the memory address and pick a byte from the cache line to send to the CPU, so we don't have to deal with main memory, right? That's what we're trying to avoid, to have to deal with the slower main memory. However, if it's a miss, okay, that's, let me get, now, we didn't have what we needed in there in the cache, so if they don't match, it's called a cache miss, and we use the 22 bits tag part of the address from the CPU to get the 4-byte block from memory and put it in the cache. So that's we're replacing. I haven't talked about the what we're kicking out of the cache yet. That's a whole different thing. The replacement algorithm. But just on these examples right here for mapping, we're just getting something and we've kicked something out of the cache and we're putting something new in because we've had a miss. And simultaneously, we get the byte from memory pointed to by the full 24-bit address from the CPU, and just go get it. So, just as if you didn't even have a cache, if there's a miss, you go in the CPU and you're going to the main memory and getting what you need for the CPU. However, you're trying to fix the problem that the cache didn't have what you needed. It's not a problem. It's not an error. It's the cost of trying to do speed-up measures. There's a probability involved here of whether or not you're going to have something that you need in there. And it's one of the reasons probability theory is so important. I'm going to say theory, probability, and statistics is important in computer engineering curriculum. Now we will look at set associative mapping, which is a compromise between the pluses and minuses of both the direct and associative cache. And so that we're going to divide, the cache is divided into sets, and we'll see how that works. And it's referred to as a k-way set associative, just like when we talk about superscalar, it's k-way. For parallel pipeline, this is k-way because there's 2 essentially parallel sets. And then they repeat here in this slide the disadvantage of fully associative, and now this is going to be more of an advantage, so you don't have to compare all the tags.
This is now set associative, and for this example, 2-way set associative. So the 2 means that the sets each contain 2 cache lines. And so first you want to find out which set to look at, and then compare the cache lines, the tags in each of the cache lines to the tag in the thing coming from main memory. So we have first to figure out the tag, we need to deduct from the length of the word coming from memory 2 bits, so we can pick a byte within a line once we have something to look at, and then we calculate or subtract also the number of bits for the sets, picking sets, and then what's left is the tag. So then the tag you can see is that amount, and that tells us how to parse up memory. And so when you how the thing functions is when you the CPU is trying to access from main memory, and hopefully maybe something's in a cache or in this cache to make it faster of an access. You first pick a set to look at based on the bits that are set aside for this set, and then you have a pair of cache lines that you look at, and then you compare the tag coming from main memory to each of the tags in that set that you've selected, and then if it's there, that's a cache hit, and you look more deeply into the line that you had a hit for, and you get the byte out of that based on the 2 bits that are in this word. And then if there's a miss, then you do as before, and you replace something in the cache, and then simultaneously go to main memory and get what main memory needs. It'll be slower that way because you were hoping it was in the cache, and it wasn't, so you had to go to main memory.
Now, on the following pages, you will see in handwriting a student's, one of my teaching assistants from several years ago, writing down what I was writing on the board when I used to not have a PowerPoint or any kind of presentation online. This first narrative version that we're doing is because school was canceled in class because of the coronavirus. Perhaps when you're listening to this, it was history. Right now, it's not. It's happening as this is being recorded. But anyway, take a look at these same 3 examples and compare and contrast as you go through, and think about the tag size. Think about how memory lays out and how the cache is a little bit different for each. Think about how each of them works a little bit differently. Think about how on both cache hit and miss, it's a little bit different for both. In all cases, all 3 of them, there's a similarity in that you're getting, if on a miss, you're replacing something in the cache, and you're getting a chunk, a block, because of spatial locality of reference, right, and of probability of needing what you'll need next is a chunk, either an instruction in a construction segment or data in an array. So a chunk, and you're putting that in the cache, and simultaneously on a cache miss, you're getting specifically what the CPU is asking for. You're not putting the whole chunk into the CPU. On the following 6 pages, you're going to see from 2 different texts, the same 3 examples of mapping compared with the slightly different graphics. So just take a look at those and ask yourself how the imaging looks a little different. Look at the arrows showing what's being mapped to the cache slots, cache lines, what blocks from memory are being mapped, and look at the main memory address up above and how it's being parsed in tag and block and word. And compare the 3 different techniques. The last slide had direct, and then this is fully associative. This is set associative. And here are the same 3 mapping techniques on the next 3 slides. Can be compared from a third source, textbook, I believe I got from 3 different textbooks I remember from the past. And this is the direct mapping in that third text. The fully associative in that third text. And the set associative, the 2-way set associative in that third text book. This slide is mostly reference information with first comparison of some historical computers of the past with cache size and set size and number of sets. And then a little narrative about a sector mapping cache, which is a 4th way of mapping, which we will not cover in this course. But you're welcome to look into it a little more if you like. And it is actually shown on the next slide here. So you can take a look at that if you like, but I will not test in this particular course on that for the sake of time. And this is a rather very large and long lecture that I'll probably parse into several lectures in the future, especially with the audio embedded now. Now we need to consider what we do in the cache if we have a cache miss, and then we're going and we're getting a new block out of memory to put in the cache, with what we were looking for that wasn't in there, and so we're now replacing something, and so we have to decide what to put in there. Now with the direct map, there's no replacement algorithm because it's obvious where it goes. There's a designated line slot for each thing to go in for main memory. However, for the fully associative and set associative, you need a replacement algorithm. So there's something to consider too. And this algorithm is in hardware to be fast, right? You can do algorithms in hardware. I did quite a bit of that in IBM. And that's where the fastest things are going to be. So there's different replacement algorithms. So the first is least recently used, and so you replace the block in the cache longest with no references. And then the second one is a FIFO, first in, first out. Probably know from my data structures or some other place. Replace the block that's been in the cache the longest. This is not without reference, it's just the longest. And then the C here, number C, is the least frequently used. And then random, just random, is the fourth. So in this course, just be able to list them and define which each is. So certainly don't need to make a hardware algorithm here. I had thought about making a lab for this project. I may still, but there's a lot of complexity. And then it gets even more complex where you start worrying about cache coherency. So this write policy is the next thing. And this gets very hairy. This is where I had to write a whole program and a whole study for multiprocessor systems here. And so we're just going to kind of touch on this a little bit. If you're writing back into main memory, or I mean, if you're changing something in the CPU and then you're writing it back to your cache, there's a number of things you can do. You can have a write-through policy, and then in that case, you're writing it right back through memory and changing memory, and then the other caches just have to keep track of that happening and then invalidate if they've actually grabbed that piece. And then you have, so that's write through, and then you have write back, minimizes memory writes. Updates are made only in the cache, and when an update occurs, an update bit associated with that line is set, and then when a block is replaced, it is written back to main memory, and if and only if the update bit is set. The problem with writeback is the portions of the main memory are invalid, and hence accesses by I/O modules can be allowed only through the cache, and that's a whole other thing there. This makes for complex circuitry and bottlenecks and very complex analysis and design. And then write once policy, I think that wasn't even written in this particular text. I had a whole other very expensive text I bought inside IBM just to fully understand the principles, and then actually have to go in and change the hardware. So write once policy, part of a complex cache coherency policy, skip for now. I can direct you towards more information if you would like on that. It's not something you want to do in an undergraduate course, really. Now there's a very important concept here, and I'm debating actually making this whole lecture into 3 completely separate lectures and elaborating on this. And this is where probability comes in a big way. your line size, your block size, and there, as the line size, block size increases, your hit miss ratio first goes up a little bit, and then you get a little bit less for each little increment of line size, and then you actually start to lose after a while in performance. And so this is like in economics, you've heard of the law of diminishing marginal returns, perhaps. So you see on this curve here, as the block size increases, um, the hit ratio will first start increasing because of the principle of locality of reference, spatial locality of reference, and temporal. Actually, it's both, and which states that the data in the vicinity of a reference word, which is the spatial, is likely to be referenced in the near future, which is the temporal part. And as the block size increases, more useful data is brought into the cache. The hit ratio will begin to decrease, however, as the block becomes even bigger and the probability of using the newly fetched information becomes less than the probability of reusing the information that has to be replaced. So and then there's two specific effects come into play. So I want you to think about this a little bit because this is important. Larger blocks reduce the number of blocks that fit into a cache. Right? You only have a certain size cache, so the blocks are too big. You're going to fit less cache blocks in there. You have less lines in the cache to put blocks in. And it results in data being overwritten shortly after it's been fetched, right? If you have less blocks. Therefore, part of that first part. And then secondly, as blocks become larger, each additional word is farther from the requested word and therefore less likely to be needed in the near future. That's interesting too. So like our examples just had very small blocks, sizes, but if you have really big block sizes, then maybe you're bigger than the average code segment if there's instructions in there in a loop, and it's bigger than a loop, or reusable code segment that's being called over and over again, subroutine or whatever, or it's in a data array and you're just too many bytes that for the average chunk of an array. We're talking about very big blocks here. So those are that whole thing's very important, and I almost certainly will want you to know that and test maybe. And so finally here, as possible cache sizes increase, this is what you want to do: increase the number of cache lines first, and then consider increasing the line size a little bit. It's a general overall principle. On this slide, you see a graph, that third graph, number C, is what we were just talking about, of block size versus the hit ratio, and then above that, hit ratio versus cache size overall, the overall cache size, and then another third graph up above. We could look at this in statistical sense, and I could show you some data on all that, but that would make this lecture already more monstrous than it already is. This file's getting humongous.
Now, we typically have a number of levels of caches, with the ones L1 would be closest to the processors. Also L0 sometimes you'll see in present Nvidia chips as well as in IBM chips that I helped make in the 1990s. But L1 is faster and smaller, a static RAM, closer to the processor. L2 is not as small, but bigger. L3 is even bigger. And so this level of caching has been around for quite a while, and there's good reasons for that. And then also you can have a split instruction cache between data and instructions, or a unified cache. Now in 2025, we want to look at the difference between CPUs and GPUs. GPUs are much more than just for graphics nowadays. All of deep learning and AI works on them. And so a CPU cache is what we've been talking about so far. A GPU cache is more for optimizing parallel threads, It also works now in conjunction with other aspects of memory management, including compression techniques and the Nvidia chips, which we'll talk about in a second. So the Nvidia caches has an L1 and L2, and they're made more for parallel processing, the threads and the computations in neural networks, which are linear algebra vector register kind of updates, multiply accumulates, dot product, row times column and matrices, and then summing those up and input into a transfer function of a neuron. And then here's just some graphs that I had talked about in previous lectures with the students, but putting on here again. This is in 2025. The H100 is the highest performing. This is 2022 trade restrictions, 2025 in the beginning, and just recently in April of 2025, as I'm recording this, about a week ago, the H20 was put into the export controls. So China cannot use these. I've talked about DeepSeek and how they did a workaround here when they had restrictions in here. And now this is kind of a follow-up of that because of DeepSeek's ability to use workarounds on the limited processors that they got a hold of here, the 800s before the restrictions, and including mixture of experts and distillation processes. And so now we're also concerned about, on this graph, you see connectivity bandwidth on the x-axis and performance on the y-axis. So it's not just the overall floating point operation performance that is of concern, but also the connectivity bandwidth, and cache certainly speaks to that. And so here you can see some details of the H100 chip, again, the highest performing chip at the moment here in April of 2025. The A series was before that at Nvidia, and then the H series of the H800, 100, and recently 20. Then you can see how they combine here the L1 cache with tensor core and essentially high-speed memory management of this whole overall architecture that they speak of here, and high bandwidth memory. And using PCI Express, which I talk in my lower level courses about. But if you don't know what that is serial communication in parallel. So parallel serial lines, and this came about 20 years ago, where everything used to be in parallel within PCs, for example, not in higher performing machines. And then the idea to go serial and do that in parallel.